Thanks, Clive. Right, everyone, let's get started. Can you all hear me okay at the back? Okay. Right, so we're up to page 35 of the manuals. Can I just check that everyone does have a manual now? Right, so this week's topic is correlation and regression. Okay, but as usual, we will just have a very brief recap of what we covered last week, okay, to consolidate the knowledge. Now, in lecture 3, we introduced the notion of hypothesis testing, okay? But we came back to that topic in lecture 4 because it was one of the more complex subjects, okay? So we looked at 2 sample t-tests and paired t-tests. Now, obviously, in your own research, okay, or in your own work in future, you will have to decide, okay, do I carry out a 2 sample t-test or a paired t-test? Okay, you won't be told, you'll have to decide. So, what are the considerations that you make when you pick a statistical test? Okay, let's look back to one of the data sets that was not marine, in nature. Okay, columns A and B. Okay, 10 boys, 10 girls. They take and examine maths, and we would like to not just understand what's happening here with these 20 children, we want to draw a conclusion about maths ability. Okay, we want to compare gender for maths ability. Okay, who's the best at maths? So, what would be the considerations that you would make before picking the test? Okay, firstly, what is the right test? Is it the 2 sample t-test or the paired t-test? Okay, so it's the 2 sample t-test. Okay, whereas over here, okay, 10 boys take and examine maths in year 1. The same 10 boys take and examine maths in year 2. Okay, we know that the right test is what? The paired t. So, what are the considerations that you make? How do you know these are the right tests? Okay, the first topic that we covered in lecture 1 was data types. Okay, there's 2 words, both beginning with Q. What are those 2 words? Quantitative and qualitative. So, what information has been collected here for these children? Is it quantitative data or qualitative data? The data type would be quantitative, okay? So your first consideration when picking a test would be, data type? Is the data type quantitative or qualitative? Okay, second consideration. Columns A and B. Okay, how many samples have we got? Well, the name of the test, we know it's a 2-sample t-test. There's clearly 2 samples. But again, for the 10 boys, would you agree that you see 2 columns? Okay, 2 columns of numbers. Okay, so with both these tests, you see 2 columns of numerical information. So, what's your third consideration? Your third consideration would be, would you agree, are the samples paired or unpaired? Okay, why do we say that these samples here that I've highlighted, why are they paired? They're paired because the cells I've highlighted here, okay, these 2 values, they relate to the same child, the same boy. Would you all agree? Okay, that's boy 1 scores in year 1 and year 2. So this information is paired. Over here, the cells I've highlighted, there's no link, is there? Okay, that's boy 1 score and girl 1 score. Okay, no link. The columns, the samples are unpaired. What's your final consideration? What's the assumption of the t-tests? I'm thinking of a word that begins with N. The assumption of the t-tests, a certain distribution, the normal distribution. So your final consideration when picking a statistical test would be, is a distribution assumed? Okay, the normal distribution is assumed for the t-tests. Okay, so consideration 1, data type. We're dealing with numerical information, aren't we? Quantitative data. Okay, what were my 2 questions over the last 2 weeks on the discussion boards? What is the equivalent of the 2-sample t-test if you've got categorical data? And Yulia answered with the chi-squared test. Okay, so it's not in the syllabus for 8064, so don't worry about it, but you might need it in future. Okay, last week I asked you for the categorical equivalent of the paired t-test. And Georgius, where's Georgius? Georgius answered with McNemar's test. Okay, so there are equivalents when you have categorical data. Okay, you don't need to worry though about the chi-squared test and McNemar's test. Now, this word came up last week, factor. Okay, so what is a factor? Remember that with these tests, we have independent variables and dependent variables. So what's a factor? Is it a dependent variable or an independent variable? Can anyone remember? A factor would be a factor would be an independent variable. A word that you could give to the dependent variable that you sometimes see in Minitab when you do ANOVA would be response. Okay, so if a factor is an independent variable, a response would be a dependent variable. So, I would like you just to look at the data that I've highlighted. Would you all agree that this data that I've highlighted is the same as the data in columns A and B, just stored in a different way? Okay, but when you look at the data in this format in columns D and E, it becomes easier to answer the question. How many factors have you got when you do a 2-sample t-test? How many factors have you got when you do a 2-sample t-test? We said last week the answer is 1. There is 1 factor. Now I know it's easy to think that there are 2 factors. You might guess that. Okay, it's called a 2-sample t-test. You might think 2 samples, 2 factors. You see 2 columns. But there is only 1 factor. Okay, which one's the factor? Is it column E or column D? It's column D. Okay, column D is the factor. Therefore, gender is the factor. How many levels does it have? 2. Okay, when you do a 2-sample t-test, there is only 1 factor and it has 2 levels. The question that we're trying to answer here would be, would you all agree? Is math score dependent on gender? Therefore, math score would be the dependent variable and gender would be the independent variable. So, last week we briefly mentioned this data. We didn't analyse it, but look at the data that I've highlighted. Okay, I've only highlighted 2 carpets. Okay, if you were comparing 2 carpets in terms of durability, okay, just 2 carpets, what would you do? What test would you carry out? If it's only 2 carpets, you would simply carry out the 2-sample t-test. But what if there's 4 carpets? Well, how many factors have we got here? 1 factor. How many levels? 4. Why is this test called one-way ANOVA? Because there's 1 factor. Okay, so if you've got 1 factor at any number of levels, you can carry out something called one-way ANOVA. So a 2-sample t-test is actually just a special case of one-way ANOVA. And finally, what did we say this data represented? You've got a biologist studying levels of zooplankton. Okay, a biologist studying levels of zooplankton in different lakes when different supplements are added. So, how many factors does the biologist have? How many independent variables? 2. Okay, the factors would be lake and supplement. How many levels does lake have? 2. Rose and Denison. How many levels does supplement have? 3. Why is this test called two-way ANOVA? Because there's 2 factors. Okay, so if you had 3 factors, you can do 3-way ANOVA. 4 factors, 4-way ANOVA. But really, beyond that point, okay, after 2-way ANOVA, we just say it's a designed experiment. Right, so I was asked the question in the computer practical last week. Well, I was asked the question in the computer practical last week. Well, you know, we won't be analysing lengths of birds' eggs, okay, in our own research, okay, and I understand that, okay, but I'm giving you examples, and as long as you understand what the data represents, I want you to try and transfer it to a marine application. So, here would be some marine data. Okay, I want you to imagine that we're comparing freight rates. Now, I've made up the data. When you look at it, you might not think it is very realistic, okay, for the real world, but at least you'll see it as a marine application. So, freight rates. If you would like to compare tankers and containers, okay, so just look at columns A and B. Okay, freight rates. We want to compare tankers and containers. What would be the correct test? It would be the two-sample t-test. Because, how many factors have you got? One. How many levels does it have? Two. Okay, so one factor at two levels, it's the two-sample t-test. Now, what about if you wanted to compare freight rates, not just for tankers and containers, but also for bulk? What would be the correct test? That would be a one-way ANOVA, because now, how many factors have you got? Okay, still one factor, but how many levels? Three. Okay, so that's one-way ANOVA. And finally, columns G, H and I. Again, we're interested in freight rate. Now, as well as vessel type, we have the origin of the ship. So, what would be the correct test? That would be two-way ANOVA, because there are two factors. Okay, the factors being the vessel and the origin. Okay, vessel has got 3 levels and origin has got 2 levels. Okay, so to finish off the recap, what have we said? One-way ANOVA is called one-way ANOVA because there's one factor. Okay, two-way ANOVA because there's 2 factors. Okay, so we'll look at a new topic now. Before we do, I will just mention that the project, okay, the way this module is assessed is via a project, and it has become available in Blackboard. Okay, but I'm going to explain in detail at the start of the computer practical that we'll do at 10 a.m. Right, so this new subject, correlation and regression. Okay, what I'd like you to do is just read that first paragraph. Right, so would you all agree that when you have seen previously, 2 columns, okay, of data, what we're looking at is actually the same characteristic, okay? So in columns A and B, what have we got? For the boys and girls, we have math scores. Okay. In columns H and I, okay, boy 1 in year 1 got a score in maths. In year 2, again, a score in maths. With this subject, correlation and regression, in this new subject, we again will see columns of numerical information. But this time, the variables will be different. Okay, the different characteristics. So if you look at the data that I've highlighted here, okay, I want you to imagine that for 10 people, we have recorded time on diet in months and weight loss in pounds. Okay, so that's our information. Now, in lectures 1 and 2 we talked about graphical displays. Okay, what considerations do you make when picking a graphical display? Would you all agree that your first consideration would have to be data type? Is the data type quantitative or qualitative? So, in lecture 1, we mentioned the word distribution very briefly. We talked about it more in lecture 2. Okay, but the most famous distribution of all would be the normal distribution. What are its two basic properties? Symmetrical and bell-shaped. Now, which graphical display beginning with a H looks symmetrical and bell-shaped if you've got normal data? The histogram. Okay, so we covered the histogram, but histograms aren't particularly useful when you're wanting to compare independent groups. Okay, you've got 10 boys, 10 girls who take an exam in maths. You would like to compare them graphically. What is a good graphical display for quantitative data when making comparisons? Begins with a B? Box plots. Okay, what about categorical data? What's the one that looks like a histogram? Begins with a B. Looks like a histogram, but actually it's quite different. That's the bar chart. Okay? The bar chart. Okay, the tallest bar on a bar chart is the mode. Okay, the third average. The most frequent value, the most frequent category. So, we have covered a series of different graphical displays. Okay, looking at the data in columns J and K, I want you to think of a new one. I want you to think of one that we haven't covered before. Okay, look at the data in columns J and K. And now, either individually or in pairs or groups, I want you to think of a graphical display that would be appropriate for this data in columns J and K. You don't have to know the name of it, okay, but just try to sketch it. Okay? How could we visualize this data here? Okay? 10 people, we've recorded time spent on a diet in months and weight loss in pounds. Okay, so just for the next minute, I'd like you to discuss in your pairs or groups a way to graphically visualize that data. Right, everyone, a graphical display. You might not know the name of it, or you might. Any answers? A way to visualize this data. Okay, well, I'm thinking of a graphical display that begins with an S. You definitely haven't seen it in this module, but you might have seen it elsewhere. A graphical display that begins with an S that would be suitable for this data. A scatter plot. Okay, so with a scatter plot, we have an x-axis and a y-axis. Okay, we've got two variables, haven't we? Time on diet, weight loss. So, how do we assign them to the axes of a scatter plot?
Time is always x-axis.
Okay, so it actually isn't the case that time has to be on the x-axis, but it is appropriate here. Okay, the rule would be on the x-axis we place the independent variable, and on the y-axis the dependent variable. Does that make sense to you here for this information? Which variable is dependent on which? Okay, 10 people, we've recorded time spent on diet, we've also recorded weight loss. Would you all agree, using our common sense, using our process knowledge if you like, weight loss is dependent on time spent on diet rather than the other way around? Does that make sense? Okay, so the rule would be that, there could be other instances where time might go on the y-axis if it happened to be the dependent variable. The rule would be you put the independent variable on x and the dependent variable on y. Okay, so you'll get a chance to produce scatter plots in the computer practical. So I've just produced a scatter plot of our data. Okay, so for the 10 people, we've recorded time spent on diet, that's appeared on X, and weight loss has appeared on the y-axis. So what I would say is this: scatter plots highlight the strength and direction of a relationship. Okay? Scatter plots highlight the strength and direction of a relationship. By direction, I mean positive or negative. So what's this relationship? Is it positive or negative? It's positive. I would agree, it is positive. How do we see that this is a positive relationship? Because as x increases, so does y. Okay, that makes it a positive relationship. What about strength? I said to you that scatter plots highlight strength and direction of a relationship. We've all agreed that it's positive. How about the strength? Would you say this is a strong relationship or a weak relationship? I would agree, strong, because we see a pattern, don't we? Quite clearly. Okay, so if you can see a clear pattern, okay, you would conclude that the relationship is strong rather than weak. Right, so how do we quantify strength and direction? Because as a group, we've all said that this relationship is positive and strong. But would you all agree it would be useful if we could quantify that in a number? How do we do that? We do that via the correlation coefficient. Okay, so in your notes on page 35, you are given a very nasty equation that allows you to work out the correlation coefficient. Do you need to remember this equation?
Yes.
No, you definitely don't. Not for this module. You will use Minitab. Okay, you will use Minitab to calculate the correlation coefficient. Now, just to mention some of the theory, for those of you that are particularly interested in the symbols, what was the symbol that we used for the population mean? What symbol do we use for the true mean? It's a Greek letter. mu, or me. Okay, so that's the population mean. What about a sample mean? What symbol do we use for a sample mean? X bar. Okay, X with a line above it. Okay, so would you all agree that we estimate mu, or me, by X bar? What about the population standard deviation? What symbol do we use for that? Sigma. That's right, the circle with the line off it. Okay, lowercase sigma. Okay, that's the population standard deviation. What symbol do we use for the sample standard deviation? S. Would you all agree that we estimate sigma by S? So what's our rule of thumb? We use Greek letters for the true values, the population characteristics, and we use letters from the Roman alphabet, English letters, for sample statistics. And the same applies here. Can you all see a Greek letter here? Okay, what's that Greek letter? Rho. Now rho would be the population correlation coefficient, whereas R would be, any guesses? R would be the sample correlation coefficient. Okay, think about our own research. What do we usually study? Do we usually study samples or entire populations? It's always samples, isn't it? Okay, so we would calculate R using that equation, okay, but we wouldn't do it manually. We'll use Minitab, and that will be our estimate of the true correlation coefficient. Now, although it isn't important for you to remember that equation, it is important to be able to interpret a correlation coefficient. Now, the range of values a correlation coefficient can take would be -1 to +1. Okay? A correlation coefficient can take the range -1 to +1. Okay, why is that? Why is that? Well, what have we said about correlation coefficients? What do they quantify? Strength and direction. Okay, so this scatter plot here, the direction, is it positive or negative? Positive? Strong or weak? Yeah, not as strong as before, okay? You still might say quite strong, but not as strong as before. Okay, what about this one? We're looking at recovery time and dosage of a drug. Is this positive or negative?
Negative.
Negative. Strong or weak? Okay, so we're saying fairly strong, but it's the correlation coefficient that actually quantifies that. So let's look at our data. What are we saying here? Positive, strong. So I will work out the correlation coefficient. You might have noticed there, when I used the command stat basic stats correlation, I just entered the variables, okay, in an arbitrary order. Okay, a correlation coefficient doesn't take into account which is the independent variable and which is the dependent variable. It doesn't matter. Okay, so this is the answer, 0.976. Okay, does that tie in with our thinking? Because we said this was positive and we said it was strong. Okay, how big can a correlation coefficient be? What did we say? What's the range of a correlation coefficient? -1 to +1. What would your scatter plot look like? What would your scatter plot look like if the correlation coefficient was +1? It would be a straight line. okay, the relationship would be perfect. Okay, we know this relationship isn't perfect. Okay, there's some natural random variation, but we knew it was positive and strong. So, to quantify the correlation, it's 0.976. Is that a significant result or a non-significant result? Look at the p-value. 0 to 3 decimal places. If you see a p-value that's 0 to 3 decimal places, what would your conclusion be? Highly significant, yeah? What do you do with highly significant results? What do you do with highly significant results? Do you reject the null hypothesis or do you retain it? You reject it, don't you? Anytime you see a p-value, there must have been a hypothesis test. Okay, what's the hypothesis test for a correlation? H0, that's your null. What's it telling us? The null would be that rho, okay, that's the true correlation in the population. The null is saying that the correlation coefficient is 0. Okay, what does it mean for a correlation coefficient to be 0? If +1 is perfect positive correlation, -1 is perfect negative correlation, what would 0 be? It's no correlation at all, is it? No relationship. So the null is saying that the correlation coefficient is 0 in the wider population. The alternative, that it's not 0. So our p-value was 0 to 3 decimal places. We all agree that that's a significant result, so therefore we all agree that the null should be rejected. Okay, we're rejecting this idea that the correlation in the wider population is 0 because we see such a strong positive relationship in the samples. Okay, if you just take a moment to read that paragraph on spurious correlation. Right, everyone. We said that this was strong and positive. Would you all agree a natural conclusion to draw would be the longer you spend on a diet, the more weight you will lose? Okay, so we see the relationship is positive and strong, so therefore we may conclude that X has caused Y to happen. But you need to be careful because there might be no relationship between the variables at all. This scatter plot here, I've just sketched. I don't know if you can read this very well at the back, but on the x-axis we've got firemen, and on the y-axis deaths. So I want you to imagine that for a series of fires, okay, 5 fires, we've recorded number of firemen and number of deaths. So, is this relationship positive or negative? It's positive. Strong or weak? Extremely strong. This would give us a correlation coefficient of +1. So therefore we conclude more firemen cause more deaths. Does that make sense? Doesn't make any sense, does it? Can you think of a third variable that these are both related to? The size of the fire. The larger the fire, more firemen, more deaths. So if we could hold that third variable constant, okay, if each fire was of the same size, what would we expect to happen here? We would expect the direction to change. Would you all agree? We would expect a negative relationship. More firemen, less deaths. Okay? So you need to watch out for spurious correlation. Just because you see a clear pattern, it doesn't mean that X has caused Y to happen. Now, we'll introduce this next topic, regression. Okay, what is regression? Well, I'm just going to bring up the scatter plot again that I produced earlier for time on diet and weight loss. Now, imagine that we each had that scatter plot in front of us on graph paper. Okay? And imagine that we each placed a line of best fit. Would you all agree that we know roughly where it should go? Okay? We would all place our lines somewhere similar. Okay? We know it's going to be going up from bottom left to top right. But would you all agree that we would be placing the lines in slightly different places? So there has to be a standardized procedure for putting the line in the very best place. And that procedure is called regression. Okay, you'll see in Minitab that the option to fit the line with the scatter plot is called with regression. Okay, so we will return to this shortly. I want you to look back at the notes. Okay, remember that with correlation, there was no assumption that one of the variables was dependent on the other. Okay, we do now establish dependence between the variables. Okay, there would be no point in doing a regression analysis otherwise. Okay, so we believe that y, okay, the y variable is dependent on the x variable. Okay, and we want to quantify, okay, the predictive qualities of that relationship. Okay, so this equation here, it will allow us to predict y based on x. There are certain assumptions of a regression analysis. The existence of a straight line relationship between the variables, and also that the residuals are independent and normally distributed. Now, we've never encountered that word before, residuals. Does anyone know what residuals are? Well, does anyone know what the word residual generally means in English? A residual would be what's left over. Okay, now what does it mean in regression analysis? Well, regression analysis is used to put that line in the very best place. Now, can you all see that each observation is a certain vertical distance from the line? Okay, so this point is below the line. That would be the vertical distance. This point here is above the line. Okay, that's the vertical distance. So would you all agree that each observation is a certain vertical distance from the line? Okay, these vertical distances are the residuals. Now, I want you to think back to what you said. I asked you the question, what would a scatter plot look like if the relationship between x and y was perfect? What did you say? if the relationship between x and y was perfect, the scatter plot, the points would actually form a line. Okay? The line of best fit, therefore, would just go through the points. So what would the residuals be? They'd all be 0. Okay, now in real life, we never see perfect relationships. Okay, there's always some natural variation. Okay, but we do analyse the residuals. Okay, the residuals should be normally distributed if you've got a good predictive model. So, what will we mention before the computer practical? Well, does anyone know the format of an equation of a straight line? Any straight line has an equation of a certain format. Okay, y equals mx plus c. Okay, well done. Y equals mx plus c. Don't worry if you'd never heard of that before. We've only introduced this notion now. But are you all happy with what x and y represent? What's x? The independent variable. What's y? The dependent variable. Okay, what about m? M is the slope, okay, the gradient of the line. And what about c? C would be the y-intercept. Okay, so c, well, imagine x is 0. If x is 0, well, that disappears, doesn't it? And y equals c. Okay, so c is just the y-intercept. So I've just hovered my cursor over the line of best fit on the scatter plot. Look what's appeared. I'll read it out for those of you that are struggling to see this. It says weight loss. Okay, remember weight loss is the y variable. Weight loss equals 1.693 plus 3.471 multiplied by time on diet. So would you all agree that time on diet is the x variable? So the number that you see before x, what do we know that is? The number that you see before x is the gradient. Okay, so what's the gradient of that line? 3.471. And what's the y-intercept? What's the number on its own? 1.693. Can you all see there's an r squared value? Just below that. 95.3? Okay. R squared is known as the coefficient of determination. It tells you how good your predictive model is. You now have an equation. You now have an equation that allows you to predict y based on x. But what would you want to know? You'd want to know if the model is any good. How would you quantify how good the model is? Through the r squared value. What's our r squared value? 95.3%. How big can it be? Any guesses? Any guesses how big r squared can be? It's a percentage. It can be 100%. What would that mean? If r squared was 100%, it would mean that your model was perfect. Okay? You can predict y with 100% accuracy. Any guesses what the scatter plot must look like if r squared was 100%? A straight line. There's a perfect relationship. So, in your notes, we'll just very briefly look at this. Okay, I know it's not a marine example. What we're looking at here is the number of students living in a certain town and pizza sales. Okay, so pizza sales is the y variable and student population is the x variable. Can one predict the other? Okay, so that's the information there. Your first step would be in a regression analysis to produce a scatter plot. Okay, so what would the conclusions be so far? What's the relationship between x and y? Is it positive or negative? positive, and it appears to be fairly strong. So, what if Minitab gave you this output? Okay, so students is the x variable. Is it significant? What's the p-value for students? 0 to 3 decimal places, so we would say it's a significant variable. We've also got an equation, haven't we? How do we predict sales? Well, you would multiply the number of students by 5 and add it to 60. Okay, is that model any good? Okay, does it have a high predictive quality? Well, the R² value is over 90%, so you would say, yes, that's good. Right, so I will just quickly analyse this in Minitab and we'll try to interpret it together. Okay, remember you'll get plenty of chance to do this. Okay, you'll get plenty of chance to do this in the computer practical. Okay, so we know from the scatter plot that the relationship is positive and strong. Okay, we know we've got a predictive model now that allows us to predict y based on x. But what is the assumption of regression? What do we need to check? We need to check the residuals. Okay, what are residuals? What are residuals? You need to think back to the original scatter plot. Okay, imagine a line of best fit going through the points. What are residuals? Residuals are the vertical distances that each point is from that straight line. What do these residuals need to be? Okay, these residuals need to be normally distributed. Okay, so we'll talk more about that and the project in the computer practical. Okay, so that's the end of lecture 5.
Morning. One of these days I'll ask you what you're teaching. I probably should start. That's from okay, brilliant. No, I wasn't.
Thanks a lot.
You've still got my friend.
Oh.